Hi, in this video, I'm going to explain the method of titration of an acid versus a base using a conductometer. To start with, I'll explain some basic terms involved. Then I'll explain the principle behind a conductometric titration. Then I'll describe the construction and working of a conductometer along with the types of probes used in a conductometer. Then I'll explain the method of standardization of a conductometer. And finally, I'll explain the method of determination of the endpoint of the titration using the graphs obtained from the data of the experiment. Now, some of the basic terms involved are conductance, specific conductance, molar conductance, equivalent conductance, and cell constant. I'll start with the definition of conductance. Basically, it is the reciprocal of electrical resistance. It also describes the ease with which current can flow through a solution. So if I denote conductance as C, in that case, it can be represented as reciprocal of R, which is the resistance of the solution. Now, at the outset itself, I would like to point out that a conducting solution can obey Ohm's law beyond its decomposition potential, and as a consequence, the current through the solution will be directly proportional to the conductance or inversely proportional to the resistance. This is a simple formula which I am sure you all have come across earlier, which relates resistance, the length of a conductor, and the area of cross section of a conductor. So this formula is R is equal to rho L by A, where rho is the resistivity of the material, L is the length of the conductor, and A is the area of cross section. This formula clearly tells us that resistance is directly proportional to the length of the conductor and inversely proportional to the area of cross section. Now, since conductance is the reciprocal of resistance, we can say that conductance is directly proportional to the area of cross section and inversely proportional to the length of the conductor. So basically, the earlier formula I have modified and written it as conductance is equal to a constant into area of cross section divided by length. This constant, which is symbolized as kappa, is called the specific conductance of the conductor, and obviously it is the reciprocal of the resistivity or the specific resistance of the conductor. Also, I may bring it to your notice that as far as electrolytes are concerned, we always talk about their conductance rather than their resistance. Now, there are several units of conductance, and all these units are equivalent. So one of the unit is mho, which is ohm spelled the other way around, or ohm inverse, or the modern day unit is Siemens. All these units are equivalent in the sense that 1 Siemens is equal to 1 ohm inverse is equal to 1 mho. Now, specific conductance or conductivity of a solution can be denoted as kappa, and it represents the conductance offered by unit volume of a solution of an electrolyte. So basically, it's a conductance of a solution which is placed between two electrodes 1 centimeter apart and having area of cross section 1 centimeter square. In that case, the volume of the solution involved is 1 centimeter cube. So I'll repeat, specific conductance or conductivity is nothing but the conductance of 1 cm cube or unit volume of a solution. As I pointed out earlier, that specific conductance is the reciprocal of resistivity. Now, units of kappa. So I've rewritten the formula which I've shown you all earlier. We can always write conductance as reciprocal of resistance. And in that case, since the unit of conductance is Siemens, the unit of length is centimeters, and unit of area of cross section is centimeter square, we can represent the unit of specific conductance or conductivity as Siemens per centimeter. And if we take the length in meters and area of cross section in meter square, then obviously we can also write the unit as Siemens per meter, which will be the SI unit of conductivity. We can always replace Siemens as mho. The SI unit is obviously Siemens per meter. Now the next basic term, which is molar conductance. So molar conductance is a conductance of a solution which contains 1 mole of an electrolyte when it is placed between two parallel electrodes unit distance apart, so maybe say 1 centimeter apart, and having cross-sectional area large enough to accommodate the entire volume of the solution. So that means the cross-sectional area has to be so large that it has to accommodate the entire volume of the solution. Obviously, this is an hypothetical quantity, as it will be difficult to construct an electrode having a large cross-sectional area in order to determine the molar conductance experimentally. Now let's see the formula for molar conductance. The molar conductance is represented as kappa into 1000 upon C, where kappa is obviously the conductivity or specific conductance and C is the concentration of the solution. In this case, the concentration of the solution is generally taken in moles per dm cube and kappa is represented as Siemens per centimeter. So as a consequence, the unit of molar conductance is Siemens centimeter square per mole or Siemens meter square per mole. Now equivalent conductance is a term which is quite similar to molar conductance. The only difference being that instead of taking 1 mole of an electrolyte in the solution, 1 gram equivalent of an electrolyte needs to be taken. So obviously equivalent conductance similar to molar conductance can be defined as a conductance of an electrolytic solution containing 1 gram equivalent of an electrolyte when placed between electrodes 1 centimeter apart, say unit distance, and having cross-sectional area large enough to accommodate the entire solution. So lambda equivalent, that is the equivalent conductance, can be represented as kappa into 1000 upon C, where C is the concentration in gram equivalents per dm cube, that is technically it is the normality of the solution, and kappa is as usual measured in Siemens per centimeter. So the unit of equivalent conductance can be written as Siemens centimeter square per gram equivalent or Siemens meter square per gram equivalent. Now, what is the principle of conductometric titration? So when you mix two electrolytes and suppose there is an ionic reaction which happens, in that case there will be a sudden change in the conductance of the solution, and this change can be utilized to determine the end point of the titration. Now let's see how a conductometer looks like, works, and what kind of probe is used in a conductometer. So this is a simple conductometer in front of you all, and the probe will be dipped into the solution whose conductance is to be determined. In case you need to stir your solution during a titration, then there is a magnetic stirrer available, and in that case the solution to be stirred will have to be kept on the top of the conductometer. This is obviously the on-off switch, and this knob represents the range in which the conductance reading can be taken. So in case your solutions have very poor conductance, then the readings can be taken in micromhos or microsiemens range. So in that case, this particular knob can be placed in the lower range, and in that case the readings shown on the display will be readings in microsiemens or micromhos, and hence if you need to represent it in Siemens or mhos, you will need to multiply them by a factor of 10 raised to minus 6. However, the solutions that we use for our regular titrations have conductance in millimhos range, and hence will be either taking a reading at a range of 0 to 2 millimhos or 2 to 20 millimhos or from 20 to 200 millimhos. This is a switch required for standardization of the conductometer. As you all can read it clearly out here, that it says that when you put the switch down as indicated by this arrow, the standard conductance will be 1 millimho. Since this switch is already down, as you all can see, it is 1.000. So 1 millimho or 10 to the power minus 3 mhos. This is the experimental setup. So you can see the probe connected to the knobs out there and finally dipped into the solution whose conductance has to be determined. And since we are carrying out a titration, we'll need a burette which will be filled up with the titrant. The circuit inside a conductometer is that of a simple Wheatstone bridge. And as you all know very well, this bridge can be balanced. The current through points 2 and 4 will be 0 and the voltmeter would be indicating 0 current. The ratio of the resistances Rm to Rb will be the same as that of Rf1 to Rf2. So what we do is we make one of the electrolyte solutions or the electrode solutions as one of the resistors in the Wheatstone circuit bridge. From chemistry point of view, we are not interested in any other kind of circuitry involved for the same. As you all can see very clearly, the probe is dipped into the solution. Now what we do is initially we rinse the probe with water and pour into this beaker the solution which has to be titrated. However, many times the volume of the solution taken will be very small and as a consequence the probe may not dip completely in the solution. In that case, we can add a random amount of water into the beaker in order to make sure that the electrodes of the probe are dipped in the solution. So basically, if I am carrying out a titration of say HCl versus NaOH, this beaker will have a small amount of HCl which becomes the analyte. However, the electrodes of the probe may not dip in HCl solution. And as a consequence, we will add a small amount of water in order to make sure that the electrodes are dipping in the solution. Obviously, you can see out here that the standardization switch is still down and as a consequence, the display shown out here will not budge from 1.000, although there is a solution in which the probe is dipped. So basically, the conductometer is not responding to the probe and showing a reading of 1.000 millimos or millisiemens. So before we start the experiment itself, we need to put this knob up. In that case, the probe and its solution will be brought into the circuit and the display will show the reading of the conductance of the solution in millimos or millisiemens. Similar diagram out here. Now, what is the probe of a conductometer? So the probe of a conductometer is called a conductivity cell and it consists of a glass vessel with two electrodes at a definite distance apart and it is filled with a solution whose conductivity is to be determined. So as you all can see through these holes, there are two plates inside and the reading taken is that of the solution standing between the two plates. The outer plastic jacket is just a protective jacket and these two electrodes are made up of platinum and the inside part are coated with platinum black. You can have a 2 electrode conductivity cell or a 4 electrode conductivity cell. However, in our lab, we are generally going to use the 2 electrode conductivity cell, which consists of 2 platinum electrodes as I have told you all earlier, which are out here, and the inside of each of these plates is coated with platinum black. Now let's learn the concept of cell constant. Obviously, the cell constant is a term related to the probe used in the conductometer. So cell constant is a ratio of the distance between two electrodes and the area of cross section of the electrode. Since it represents length upon area of cross section, the unit will be centimeter upon centimeter square, which is centimeter inverse. In that case, if you look at the formula, kappa is equal to L by A into conductance, then L by A itself is the cell constant. So we can safely say that kappa is cell constant multiplied by the conductance of the solution. To standardize the conductometer, we need to put this switch down and put the range at 2 millimos, as you all can see. Now, in that case, the display will show a reading of 1.000. However, when you need to take the readings, probably you will need to move from 2 millimos to 20 millimos as the conductance of the solution itself may be more than 2 millimos. The reading on the display to be represented in mhos or Siemens we need to multiply each and every reading on the display by 10 to the power minus 3 in order to represent it in either Siemens or Mohs. One more thing, I had shown you all a stirrer on the side earlier. If you need to use this magnetic stirrer, then place the beaker on the conductometer and you will have to put a magnetic bead inside the solution and then switch on the magnetic stirrer. To start off with the readings, this switch needs to be placed up so that the solution in the beaker comes into the circuit and the display shows the conductance of the solution. Also, since we are carrying out a titration, we'll need a burette which will be filled up with the base, as analyte here is an acid. Now we are ready to take the reading. So what can be done is, we can add from the burette about 1 ml of the solution, stir this solution and take down the reading on the display. So what we are going to do is, throughout the titration, we are going to add the base from the burette in installments of 1 ml each, and after adding every installment, we are going to stir the solution with the help of a glass rod and taking down the reading after addition of each installment of NaOH from the burette. After this, we need to plot the graph of conductance versus volume of NaOH added from the burette. So obviously the conductance data is obtained from the conductometer itself. Now let's look at the graph for titration of a strong acid versus a strong base. If you look at the ionic reaction, technically only H plus ions have reacted with the OH minus ions to form water. So initially when you have HCl, the conductance is quite large due to availability of large number of H plus ions in the solution. However, as NaOH is added from the burette, the H plus ions from HCl will react with OH minus ions from NaOH to form undissociated water. Now, as a consequence, as we add more and more NaOH from the burette, the concentration of H plus keeps decreasing, and as a consequence, the conductance of the solution keeps decreasing as shown out here. However, once we have reached the end point or the equivalence point, then as only NaOH is being added to the solution, the conductance of the solution will again increase. So the end point or the equivalence point can be determined by extending these two graphs and extrapolating a line from where these two graphs meet to the x-axis, which is volume of base or NaOH added to the HCl solution, and therefore this point will represent the end point or the equivalence point. Look at this graph. This is obtained when a weak acid is titrated versus a strong base. For example, acetic acid is being titrated versus NaOH. As you all can see, the H plus ions will combine with OH minus ions in the previous case to form water. Now initially in the beaker, we are going to place a small amount, maybe about 10 ml or 25 ml of acetic acid. And then, as I told you all, we are going to add NaOH from the burette in installments. Take the reading from the display and note it down. Now, initially therefore, there's a large concentration of acetic acid and its conductance is not very high like that of HCl, because acetic acid is a weak acid and does not dissociate completely. As NaOH is added from the burette, initially the conductance of the solution is going to drop. This is because when NaOH is added from the burette, sodium acetate salt is formed in the solution, and as a consequence, this sodium acetate being a strong electrolyte, it will suppress the dissociation of acetic acid, which is a weak electrolyte. And since its dissociation is suppressed, the conductance is initially going to fall. However, as we add more and more NaOH from the burette into the acetic acid in the beaker, there is more and more salt, which is sodium acetate, that is formed, and it contributes largely to the conductance of the solution. So as a consequence, the conductance of the solution will increase. And however, once the endpoint is reached, there is no acetic acid left behind in the beaker, and as a consequence, a large amount of NaOH is being added to the beaker. Consequently, its conductance will go higher up. We can even titrate a weak acid versus a weak base. Go over this graph and try and explain the shape of this graph. Also, apart from that, we can take a mixture of a strong acid and a weak acid. For example, we can take a mixture of HCl, which is hydrochloric acid, and acetic acid, and titrate this mixture against strong base like NaOH. In that case, initially you will find that the conductance is quite large due to presence of HCl, or you can think of it as presence of H plus ions. However, as we add more and more NaOH from the burette, the strong acid will get neutralized. Finally, the next installment of NaOH will start neutralizing acetic acid, and then at the end of it, when no more acetic acid is left, the conductance of the solution will shoot up due to presence of NaOH, as OH minus ions have a very large conductance. Question time for you all. What kind of current, DC or AC, that is direct current or alternating current, is fed to the probe or the conductivity cell of a conductometer, and why? Before the titration, to the solution taken in the beaker, random amount of water is added so as to dip the electrode completely in the solution. Don't you think in that case, this random addition of water will change the concentration of the analyte solution in the beaker, and as a consequence show a different endpoint for different trials of the experiment. Next question. The titration of a weak acid with a weak base is not possible using a visual chemical indicator. I'm sure all of you all know this. Why is this true? Also explain the reason behind the shape of the graph obtained during conductometric titration of a weak acid versus a weak base. The plot is what I've already shown you all in one of the previous slides. Now, the next one, is a precipitation titration possible using a conductometer? Then my next question, a mixture of a weak acid and a strong acid can be titrated against a strong base using a conductometer. Explain how a distinct endpoint is obtained for the strong and the weak acid. Then the next question, how will you determine the cell constant of a cell? Now the last question, does cell constant of a given cell remain constant throughout, or does it change with use? So that means I'm asking, will it change with wear and tear or not? And thank you for listening, and I hope you will be able to answer the questions before you come to the lab.